Hi. In the last video we talked about stereoisomers and you learned about enantiomers and how you can determine R and S. So if you don't remember how to do that, go back and rewatch the last video and practice. Today we're going to move a little bit further. So in the last video we talked about how molecules can be chiral, they can have a handedness to them, and that they can have stereogenic atoms, and those can be shown as R or S, depending on the direction of the bonds, the orientation of the bonds. So now we're going to ask the question of what about molecules with multiple stereogenic centers? So if you look at this seemingly simple molecule right here, you can see that there are two carbon atoms that are each bound to four different types of atoms. And so if we look at a mirror plane of this molecule, you can recognize that these two molecules are indeed enantiomers. If this molecule were to see itself in the mirror, if you flip this over, you can see that these two molecules on the top and the bottom are not the same, right? They are non-superimposable mirror images, therefore they are enantiomers. So let's take this one step further and look at what would happen if we were to try to set up the same molecule, and instead of having a perfect mirror image, we instead switched one of the bonds from going out of the board to going into the board. So now we want to ask ourselves, so this is not a mirror image anymore, but instead we have swapped just one of the stereogenic centers. So it's not a mirror, and we call these diastereomers. A quick way of looking at diastereomers is that in a case of enantiomers, you have changed both these, RR to SS, so you've swapped every possible stereogenic center. In the case of diastereomers, you've changed one of the stereogenic centers from R to S, so that's good, we've swapped that one, but the other one stays R in this case, R to R. So enantiomers and diastereomers are interesting. So enantiomers can only be detected by another chiral material. In the case of diastereomers, though, they have different chemical properties, so that means that the molecules are actually completely different. They have different polarities, they have and different reactivities often. So let's look at what I like to think of as the stereogenic or stereocenter square dance. So if we again look at these two molecules at the top, here are the enantiomers, and right below this molecule on the left is its diastereomer, where we've changed the R to an S stereogenic center here, and below this molecule we've again swapped the alcohol center from an S in this case to an R. So let's look at the relationship between these four different molecules. So again, the ones on the top are enantiomers, as we discussed last page. You flip them over and they are non-superimposable mirror images. Vertically, I've drawn these as diastereomers. Again, you've swapped one of the two stereogenic centers, but not both of them. If we look to the bottom two, these bottom two, they were diastereomers of the top ones, but they are enantiomers of each other. Similarly, if you're going top left to bottom right, they are diastereomers. Again, you've changed from RR to RS. You haven't changed both of the stereogenic centers. Bottom left to top right, you've gone from SR to SS. You've only changed one of the two stereogenic centers. One quick way of recognizing to see if you've figured out all the different possible stereoisomers, as they're called, is you can recognize that the number of stereogenic centers, 2 raised to the number of stereogenic center power, is how you figure out how many possible isomers or stereoisomers you'll have in a molecule. So in the case as shown on the left, you have 2 stereogenic centers, highlighted with this red and blue 2, and 2 raised to that power of 2 equals 4. So now we're going to look at another molecule, and I'm talking about this one specifically because it has a unique property. So it is tartaric acid. You may have eaten this, you actually probably eat this pretty frequently. It's often known as cream of tartar. So tartaric acid is an interesting diacid. There are two carboxylic acids on this molecule. And if you look at this as drawn, we could draw its mirror image. And if we wanted to go through the process of flipping this over, we would see that these two are non-superimposable mirror images of each other. They are enantiomers, so all is well and good at this point. But let's now look at the diastereomers of these two compounds. So let's see if we can fill out that rest of that square. So they look like enantiomers at first pass. We've drawn the mirror image, and let's check to see if it's non-superimposable. So if we flip this molecule over, and I'm going to highlight this carboxylic acid in yellow just to keep track of it. So if we, again, kind of did a pancake flip of this molecule over to here, we would see that actually this top and bottom molecule are indeed the same molecule. They are superimposable mirror images. So that means that it's not chiral, which is odd. So you have stereogenic centers. You can decide that these are R and S, but the whole molecule itself is not chiral. This is a unique type of molecule called meso. So again, if you have a molecule that has stereogenic centers, you can decide that they are R and S, but the entire molecule is not chiral, then you call that molecule meso. Now, an easier way than redrawing it and then flipping it is simply to redraw and rotate the bonds, and just rotate one of the bonds. So in this case, we've rotated this carbon on the left, the carbon on the right. I will re-highlight this carbon on the left to give you the frame of reference. And you can see that this molecule now has what's called a plane of symmetry. That is, if you were to put a mirror right down the middle of that molecule, the molecule would be perfectly bisected. And so again, we call this meso. This is perhaps the easiest way of recognizing a molecule as being meso, is to rotate any bonds that you're able to rotate such that you can try to look at a mirror image and see if indeed you have this perfect mirror image on both sides. Thank you for your time, and please ask any questions if you have them. Meso is a concept that often challenges students when they first encounter it. Thanks.